Welcome to sections 20.1 through 20.4, 3D kinematics. So we're going to start this video off with a review of our kinematic equations that we saw in our planar rigid body motion. It turns out that these equations largely stay the same. The biggest change is that our angular velocities and angular accelerations are now vectors. They're not just locked into what we typically considered the z or k hat direction. We're also going to be going over example 1 to illustrate these equations. Alright, so to save some time, I've kind of pre-written our equations out here, but let's just walk through them. So position is still what we've been doing before. The position to B is the position to A plus the position to B with respect to A. So again, we have two coordinate systems, a global coordinate system, and then some local coordinate system. So this would have a base point of O, and then some local coordinate system which have a base point of A. And then I can measure out to, say, this point by going from from the origin to A, and then from A out to B. So that's all that's saying. If I use a translating and rotating coordinate system, this is the most general case, then the velocity to this point out here is the velocity of the base point A, so the velocity of this red coordinate system, plus the rotation of this coordinate system, so this coordinate system might rotate, crossed with the vector 2b from A. And so you see as you rotate that, you'll get some kind of a almost tangential velocity. And then there's also some internal velocity, where this point might be getting farther out or shorter inside of this coordinate system. Acceleration will also look the same as it did for planar. So again, two coordinate systems, O, A, and then I'll have point B over here. So the acceleration of the base point of this coordinate system, and then the angular acceleration of the rotation of this coordinate system. So again, if this coordinate system is rotating like this way, if it's constant, then that term will go out to 0 most likely. If it's not constant, then we might get some angular acceleration of this coordinate system. The vector to B from A, and then this term, which is kind of a normal acceleration. It's not going to be normal acceleration per se, but it's what we've seen it before in the previous system. Our Coriolis, and then our local acceleration. So again, if I had this point accelerating, say, inward towards point A, I would pick that up inside this coordinate system. Now I can simplify this if I assume that this coordinate system cannot rotate. If I lock this coordinate system in orientation and say that it can only just translate, then I lose this term, and this term. And my equation simplified down to here. So I no longer use the rotation of this coordinate system because this coordinate system doesn't rotate. I instead use the rotation of any bars or bodies inside of this coordinate system. So I'll use a lowercase omega instead of a capital omega. Most of the time we're going to do this if we can confirm that this vector from A to B is some constant length. So like if you can think of like from your shoulder to your elbow or your elbow to your wrist, those are constant. Like they don't change in magnitude, at least not significantly. So we could use this kind of an equation set to figure out the velocities and accelerations of, say, your elbow and of your wrist. Alright, so let's apply these. So example 1, we have so I'll jump back in so you can see the full picture of it. Example 1, we have a bar rotating about this axis here, and then we have another bar rotating about this axis here. So what I'm going to do is I'm actually going to do this in a sequence. And so a lot of times robotics does this. So we're going to start off, we'll have our base coordinate system up here. And I'm also going to make our local coordinate system, A, start there as well. And then I'm going to go and find the location of point B using this coordinate system. Once I find B, I'm going to do a new problem where I set up a local coordinate system at B. This coordinate system will be allowed to rotate. The red coordinate system will not. So I'm going to use both sets of equations, and then you're going to see how these cascade into one another. Alright. So the first thing we're going to do is we're going to go find the velocity of B. So we're going to work from, say, our shoulder joint down to our elbow, and then we'll work from our elbow out to our wrist, if you kind of want to think of it that way. So we're going to find the velocity of B on our way to find the velocity of C. Remember, once I find velocity of B, I can then use that to go find velocity C. So that'll be velocity A. I'm going to establish a coordinate system up here. So we're going to draw our local coordinate system A. So I will just have this coordinate system. So that'll be our local coordinate system. I'm going to also use this point as point O. In the setup, it's important if we can make all of these ij's and k's point in the same direction. It makes our lives a lot easier. So this will be, this axis right here will be big Z and little z. It'll be big Y and little y. And then this axis will be big X and little x. Remember, big X meaning the global coordinate system and little x meaning the local coordinate system. So they're all going to be coincident in this case. They're going to be on top of each other. This coordinate system will not be allowed to rotate, but it will be allowed to translate. And I'm choosing that because this vector from A to B is fixed in magnitude. This isn't going to change. It's always going to be 1.5 meters long, so I can use this set of equations up here. So then I'm going to do VA plus omega cross RB with respect to A. So the velocity of A is fixed there. It's not going anywhere, so it's 0. My omega, the only omega I have is the omega of this bar B spinning about the x-axis. So I'm going to have a 4, and that is about x, and it is a positive. So if you use your right hand rule, if you point your thumb in the direction, if your fingers, I point my thumb in the direction of x, if my fingers curl the same way as the rotation, it's positive. If not, then it's negative. So we'll have a positive I hat for this. And then we're going to cross that with our vector to B from A. So that is all in the negative z direction. So we're going to have a 1.5, and then that's a negative in the z hat. So I could have either, sorry, not z, k hat. So you do that cross product, and you'll find out the velocity of B is 6. Well, negative 6, but we're going to cross an I into a k. So if you remember, I do this in class, I, J, K. Really only need to set this up once. So I'm going from I into K, which is going to get me to a J, but I went backwards on the circle, so I'm going to get a negative K hat. Sorry, negative J hat, sorry. I into K gives me a J. So that means I'm going to get a total of a positive 6 J hat. And if you look at that, and you imagine this thing rotating this way, so we kind of have this bar here, and it kicks up this way. Well, that makes sense. It's going to have this endpoint going that direction. So, all right, so that's velocity B. So now I can come down here to velocity B and set up a new coordinate system, which is what I'm going to do. So this coordinate system will have a base point at B. And this is how we solve robotics a lot of times, is you just work your way down through the joints. I'm going to also orient it the same way. Same direction in Z, same direction in Y, same direction in X. I would call this one X prime, Y prime, and Z prime. So little z prime. This will be a translating and rotating coordinate system because the vector from B to C will change in magnitude. So I'm going to use this equation because this magnitude is going to change. So therefore I want to use the full equation. So let me write that out. So now the velocity of C will be the velocity of B, which is the reason we went and found it in the first place, plus the rotation of the coordinate system crossed with our vector 2C from B. So just translating our equation above into this, plus the velocity of C with respect to point B in our new local coordinate system. So X prime, Y prime, Z prime. So that coordinate system. So we're using the yellow coordinate system here. I'll put a little dot so you know what coordinate system we're using here. And I'll put a little dot so you know what coordinate system we're using here. Alright. So our velocity B, well, we know that. That's just 6J. We found that previously. The rotation of the coordinate system So basically what I have is I have an IJK, and then I have B down here now. So this is point B, and I have point C out here. So this coordinate system is going to rotate like this, where it's going to rotate down through the page. So that is the 5 radians per second about the y. So it's going to be 5. Again, we'll check right hand rule. I'll point my thumb that way. My fingers curl in the direction indicated. So it's going to be a positive j hat. And again, you can call it j prime, but whatever. We're going to cross that with our vector 2c from b. So it is a 0.6. It is all in this x prime direction. So we're just going to get an I hat, and it's positive. Plus the velocity 2c from b. We were told that it's 3 meters per second along this bar. Well, conveniently, that's in this yellow coordinate system. So we're going to get 3 in the I hat. And so now what I do is I just go through. So this is still a 6 j hat. I'm going to cross a j with an I, meaning I'm going to get a k hat out of this thing. 5 times 0.6. So j and I is going to actually be a negative k hat. And then 5 times 0.6 is 3. So I'm going to get a negative 3 out of that, plus 3 I hat. So if we just rearrange this, our velocity of c, let me move my page up here so you can see everything. We're going to have 3 in the I direction, 6 in the j direction, and then a negative 3 in the k direction. And that'll all be in meters per second. So hopefully that wasn't too bad. Again, all we did is we just worked our way down. So we started at point O, built a coordinate system for A, used A to find B, then built a new coordinate system at B, and used B to find C. So we just did it in stages. And that's generally a lot easier to think through. If you have any questions, feel free to reach out.